We'll wait a couple of more minutes before starting. Do you have any doubts? If you have any doubts, you can ask in the meantime. So we'll start with the 7th week session. So this will be including the week 7 portion. So we'll have strain gauges, pressure measurement, and displacement measurement problems, and some MCQs are also there. So we'll see those one by one. And if we could answer, it will be better. We can have an interactive session. So the first question is: a mechanical strain gauge can measure A. Static strains only, B. Dynamic strains only, C. Static and quasi strain, and D. Static and dynamic strains. Can even comment in the message box, or if you can answer. I'll repeat. Mechanical strain gauge can measure A. Static strains only, B. Dynamic strains only, C. Static and quasi static strains, D. Static and dynamic strains. So the answer is static and quasi static strains. You cannot measure dynamic strains. For example, if you see mechanical, if you want to do a pressure measurement, and if you have a manometer or something, the dynamics is with respect to temperature will keep on oscillating. So the meniscus you cannot read it properly. So that kind of will have problems in that. So you can measure only static and quasi-static strains, the mechanical types. So that analogy can be put up for a mechanical strain gauge as well. So you have a strain gauge should have high value of gauge factor. A. To reduce hysteresis effect, to increase sensitivity, to eliminate the effect of variation in ambient temperature. D. To give linear relation between applied strain and resistance strain. I repeat it. A strain gauge should have a high value of gauge factor. So why is the gauge factor high value of gauge factor is preferred? So to reduce hysteresis effect, to increase sensitivity, to reduce or eliminate the effect of variation in ambient temperature, to give linear relationship between applied strain and resistance change. So basically the answer for is this is option B, to increase sensitivity. So if you remember a strain gauge, if you give the change in resistance or some, if it's measured, it will be delta R by R equals gauge factor into the strain. So if you have a higher strain gauge factor value, you will have a bigger difference in the resistance. So that will give you higher sensitivity for a given strain. So the option is answer B. Moving on to the next question, you have a quartz is a dash type of material for a piezoelectric transducer. So A. Natural and stable, B. Natural and unstable, C. Artificial and stable, D. Artificial and unstable. So what type of crystal is quartz? That's the question. So piezoelectric, we have multiple types of crystals, so out of which quartz is one. So they are asking which type of materials. A. Natural and stable, natural and unstable, artificial and stable, artificial and unstable. So for this the answer is option A, natural and stable. You see quartz is made up of SiO2 and it's a stable element, it doesn't dissociate into something else. So SiO2, it's a stable compound, and we have hexagonal structure for it, and it's a naturally forming crystal. It's not artificially made, it's not made by humans, so it's naturally occurring. So quartz is a natural and stable material for a piezoelectric transducer. Moving on, we have which of the following gauges can be detached from the test specimen and used again. A. Semiconductor gauges, B. Metal foil gauges, C. Bonded metal wire gauges, D. Unbonded metal wire gauges. So the question is, what type of gauge can be removed or put up again and again? You can remove it, then keep it back to test, measure the specimen strain. So what type of gauges are those? So A is the semiconductor gauges, B metal foil gauges, C is bonded metal wire gauges, D is unbonded metal wire gauges. So the answer is option D, unbounded metal wire gauges. So the rest of three is fixed on the specimen. You cannot remove it once you are fixing it. So see, if in this case bonded, you bond that to the specimen. It's like fixed. In the unbounded, you have two types. The unbounded wire gauges are made up of two frames. You have one frame and the other frame. Both are linked with a wire or any spring mechanism, which will measure the force. So when the frames move relative to each other because of the force, so the wires will get elongated or compressed, which will cause a change in resistance or length, and which is measured, and that is used to measure the force. So this type of gauges are called unbounded because you can remove them and keep it at your, if you want, you can put it again back again and you can remove, and so that is those are called unbounded. So the name says, you can say it's not fixed to the specimen. So that's why it's unbounded metal wire gauges. So the answer is option B. So the next question is, the sensitivity factor of an electrical resistance strain gauge is of the order of A 1 to 1.5, B 1.5 to 2, C 0.5 to 1, D 5 to 10. So been asked the sensitivity factor, what is the order of the sensitivity factor for electrical type resistance strain gauge. So order is 1 to 1.5. The options are 1 to 1.5, 1.5 to 2, then 0.5 to 1, then 5 to 10. So for this, the answer is option B, 1.5 to 2. So if you go with the different semiconductor type, the sensitivity can be higher. For normal electrical type strain gauges, the order sensitivity factor order lies between 1.5 and 2. So moving on, we have a question: a strain gauge with a nominal resistance of 120 ohms. So we have a strain gauge with a nominal resistance, with it unstressed or R0 value is 120 ohms, and a gauge factor is of 2, which undergoes a strain of 10 power minus 5. So strain is given, you have no gauge factor, you know the resistance of the strain gauge, which is 120 ohms. So we have been asked, what is the change in resistance in response to the strain. So strain gauge with nominal resistance of 120 ohms and gauge factor 2 undergoes a strain of 10 power minus 5. What is the change in resistance in response to strain? A 24 ohms, B 240 ohms, C 2.4 into 10 power minus 3 ohms, and 2.4 into 10 power minus 2 ohms. So this is a simple calculation. So we have been asked to calculate what will be the change in resistance in response to the strain of 10 power minus 5. This is not 10 minus 5, it's 10 power minus 5. So the answer is option C. So how will we calculate this? So in this case, we know delta R by R equals gauge factor into strain. So delta R by R is gauge factor into strain. So we know gauge factor, we know strain, which is 2 and 10 power minus 5. So delta R by R will be 2 into 10 power minus 5. So we have to calculate the change in resistance. So we will multiply by resistance. So 2 into 10 power minus 5 into resistance 120 ohms. So we will get 240 into 10 power minus 5, which will come out as 2.4 into 10 power minus 3 ohms. So the change in resistance in response to the strain of 10 power minus 5 is 2.4 into 10 power minus 3. So that will be the change in resistance. I repeat, the calculation goes the change in resistance by resistance of the strain gauge equals gauge factor into strain. Delta R by R equals gauge factor into strain. We know all the values. We have to just we need delta change in resistance. We have to substitute the other values and we can find them. Delta R by R equals F into omega. So the next question is, the U-tube differential manometers are not suitable for dynamic signals. A, B, accurate. C, suitable for recording. D, unaffected by gravity. The U-tube differential manometers are not suitable for dynamic signals. B, accurate. C, suitable for recording. D, unaffected by gravity. In this case, the answer is option A. It's not suitable for dynamic signals. So, as I said previously, the difference in the U-tube manometer, if it keeps on oscillating, you cannot read. So, that's one of the reasons it's not suitable for dynamic signals. But if it's a static one, it's very good at accurate and it's not affected by gravity and can record. And moving on to the next question, we have a bell type manometer is used in preference to U-tube manometer to obtain. So why is bell type manometer preferred compared to the U-tube manometer? So the options are better accuracy, B, better precision, C, high sensitivity, D, high resolution. So the reason is why we prefer bell type manometer compared to the U-tube manometer. If you remember, well type manometer is similar to the U-tube manometer, but in one end you have a bigger reservoir or a vessel type, which area is very large compared to the other end of the U-tube manometer. In the U-tube manometer, you will have throughout a U-tube of similar dimension. The area of cross section remains same. Here you have a bigger vessel and then it's connected to a U-tube. So that's a well type manometer. So in this case, this is used for the higher sensitivity. So this area difference will give you a higher sensitivity for measuring the pressure. So that's why well type manometer is preferred compared to the U-tube manometer. So moving on, in a Borden type pressure gauge, incorrect readings may be encouraged due to incorrect readings may be encountered due to. So I hope you remember the Borden tube pressure gauge. You have a Borden tube, which is an elliptical type tube with a circular. It's not a fully circular, so a circular tube, and then when you pass fluid with a higher pressure, that will get elongated, and that will give you a displacement reading with the pointer. So you can use that to measure pressure. So this tube gives you incorrect readings when encounter A, hysteresis, B, fatigue, C, creep, D, drift. So in this case, the Borden tube will give you an incorrect reading when it's coming across creep. Creep is you have a specimen with respect to time at some temperature. When it's exposed to it for a long time, that creep phenomena comes in. So that will cause the Borden tube pressure gauge to give you incorrect readings. So the answer is option C. So next question is, a piezometer tube is not used for pressure measurements in a pipeline when. So a piezometer tube is not used for pressure measurement in a pipeline when A, the fluid is highly viscous, B, the pressure difference is large, C, the flow velocity is small, and D, the flowing fluid is gas. So the question is like this: you have a pipe, you want to make a pressure measurement. You put a piezometer tube, a piezometric crystal, which is connected in the tube, and because of the pressure, the piezometric meter will get compressed or elongated, which will generate voltage. So that you measure to measure the pressure. So this type of pressure piezometer tube cannot be used to measure pressure in which of the cases. So you have a highly viscous fluid, and B, the pressure difference is large between the gauge outer one and the fluid pressure. So that is very large, and the flow velocity is small. And D, the flowing fluid is gas. So in this case, the option is answer D. The flowing fluid is gas, because this doesn't have a medium or interface to create the force, enough interface. So that's why the answer is option D. The flowing fluid is gas. Doppler shift principle is used for measurement of. So Doppler shift. There will be a shift in frequency when you pass, or you can say this phenomena is mostly used in physics and all. If you observe long range planets, so if you the light which comes out, it will have a shift. So you see in a different wavelength, frequency, which you see will be a red shift or a blue shift region. So that shift happens. So that principle is used for measuring. So the principle is used for measuring what? So A, frequency; B, sound pressure; C, speed; D, vibration. Therefore, A, frequency; B, sound pressure; C, speed; D, vibration. So the answer is option C, speed. So if you remember, you can if you in roads, if some vehicle is speeding, so a traffic policeman uses its gun type of system. You just to measure what speed the vehicle is on. So that uses the Doppler shift principle to measure the velocity speed of the vehicle. So the Doppler shift principle is used to measure the speed. So moving on, seismic transducer working in the displacement mode is designed on the basis of seismic transducer working in the displacement mode is designed on the basis of A, small mass and weak springs; small mass, stiff springs; heavy mass, weak spring; D, heavy mass, heavy spring. So seismic transducer is made up of what? They are given options on the mass and springs which are used to make the seismic transducer. So in this case, the answer is option C, heavy mass and weak spring. So if you remember, a seismic transducer have a mass and which is connected to a spring. When this mass oscillates, that is used the phenomenon is used to measure the displacement. So in this case, for a seismic transducer, you use a heavy mass and a weak spring. So we will see some problems. I hope there is no doubt in the previous questions. Okay, so moving on, a shaft transmits a maximum power of 50 kilowatt when running at constant speed of 1500 rpm. Measurements of torque are made by a pair of strain gauges which are bonded onto a specially machined portion of the shaft. Each gauge has a nominal resistance of 120 ohms, gauge factor of 2, and are connected electrically to the two arms of the half activated Wheatstone bridge circuit, which is energized with an excitation voltage of 6 volts. if the gauges have a maximum strain of 0.0015, the modulus of elasticity of the shaft material is 200 giganewton per meter square. Take shaft diameter as 1.82 centimeter. So this is what is known. We have to calculate fraction change in resistance and sensitivity of the measuring system. And repeat, the question is, you have a shaft which transmits 50 kilowatt. So you know the power of which is transmitted by the shaft, which is 50 kilowatt, and it's rotating at a constant speed of 1500 rpm. So that is also known. You have a shaft rotating at 1500 rpm, transmitting a power of 50 kilowatts. So to measure this, you have a pair of strain gauges which is bonded on a specially machined in the shaft. You have two strain gauges which are attached. So this each gauge is forming in the Wheatstone bridge the two resistances which is formed by these two gauges, and each of these gauges have a resistance of 120 ohm and a gauge factor of 2. So now, and the Wheatstone bridge voltage which is used is 6 volts. That is given, and then they are saying that if the gauge has a maximum strain of 0.0015, then we have to calculate the change in resistance and the sensitivity. And we have also been given the shaft diameter as 1.82 centimeter, and the modulus of elasticity of the shaft material is 200 giganewton per meter square. So to calculate fractional change in resistance and sensitivity of the measuring system. Please try to solve this. So we'll see how this is solved. So for fractional change in resistance, as I already mentioned in the previous problem, this is the change in resistance by resistance into gauge factor into strain. So we know gauge factor, we know strain. So gauge factor is 2 and strain is 0.0015. So that is 3 into 10 power minus 3 for percentage, you can say, or a fraction change of resistance. So that is 3 into 10 power minus 3 or 0.3%. So from the option, we have a fraction change in resistance as option A, 3 into 10 power minus 3. So the answer is option A for the first part of the question. So the next part is you have to find out sensitivity of the measuring system. In this case, the output voltage of an equal arm bridge used for the half activated bridge, from there we know that this is 2 times dr by r into the supply voltage by 4. The change in voltage is 2 times change in fraction change in resistance into supply voltage by 4. So from there we substitute fraction change in resistance there in the equation, and we know supply voltage is 6. So 2 into 3 into 10 power minus 3, this is 3 into 10 power minus 3 into 6 by 4, that will give you 9 millivolts. So the output voltage of the Wheatstone bridge will be 9 millivolts. So from there we know, here it's given as the shaft transmits a maximum power of 50 kilowatts. So for 50 kilowatts we have 9 millivolts. So the sensitivity will be change in voltage by the power transmitted. Per kilowatt it will be 0.18 millivolt per Kelvin. So the sensitivity is 0.18 millivolt Kelvin, millivolt by kilowatt. So that is the overall sensitivity. So from the question, it's the answer option B, sensitivity of measuring system. So moving on, we have a torsional dynamometer which is used to find the power of the engine. The solid propeller shaft having 20 centimeter diameter twists 2 degree. Please note this is 2 degree in a length of 6 meters. If the modulus of rigidity is 80 giganewton per meter square, and if the shaft runs at 500 rpm, find the horsepower of the engine in kilowatt. So you have an engine, you have to measure the torque. So use a torsion dynamometer. They say the propeller shaft is of 20 centimeter diameter, which twists by 2 degrees. So theta is 2 degrees, and the length is given is 6 meters. We know the modulus of rigidity G as 80 giganewton per meter square, and the shaft is running at 500 rpm. So find the horsepower of the engine. So you need to find out the power of the engine. So in this case, if you see from the relation, we know T by I is C theta by L into tau by R equals tau by R. So the T by I equals C theta by L equals tau by R. Tau is the shear stress, R the radius, and you have C modulus of rigidity, theta the angle of twist, divided by length, and T is torque divided by polar modulus of moment of inertia, polar moment of inertia. Then as we know, this is a circular shaft of diameter 20 centimeter. We know that polar moment of inertia is Ixx plus Iyy by 2. So in this case, Ixx and Iyy will be same, as this is a symmetric one, and we know molar moment of inertia of circle is pi by 64 d raised to power 4. So we take twice of that, Ixx plus Iyy. So we have pi d raised to power 4 by 32. So polar moment of inertia of a circle is pi d raised to power 4 by 32. So we substitute the diameter as, we know 20 centimeter, which is 0.2 meters. So we substitute that, divide by 32. So we get 1.57 into 10 power minus 4 meter raised to power 4. So that is the polar moment of inertia. Then we know angle of twist is 2 degrees. So we convert this into radians, which is 2 into pi by 180, which gives you 0.035 radians. And when substituting this into the above relation, T equals to polar moment of inertia into C theta by L, we know polar moment of inertia 1.57 into 10 power minus 4 into moment of modulus of rigidity as 80 into 10 power 9, which is given 80 giganewton. Giga is 10 power 9, and then theta in radians is 0.0349, divided by length is 6 meter, which is given. So substituting that, we get 73057 Newton meter. So this is the torque. So to find out power, we need to multiply by omega. Omega is 2 pi n by 60. So just like for torque into angular velocity omega, so T into 2 pi n by 60. So we get, we know n rotation is 500 rpms, so we convert it into seconds by 60. that's why we divide by 60 into we need in kilowatt, so we divide it by 1000. So 2 pi into 500 into 73057 divide by 60 into 1000, so which gives you 3823 kilowatts. So from the question, its answer is option B. So I hope this is clear. We just use the relation for finding out torque. We found out polar moment of inertia. The rest of it is known. We substitute the values, we find out torque. We substitute it into power relation 2 pi mt into pi 60, and we get to the power, which is 3823 kilowatts. So moving on, the next question is, we have a U-tube manometer which employs a special oil having a specific gravity of 0.82 for the manometer fluid. So the manometer fluid is oil with a specific gravity of 0.82. One side of the manometer is open to local atmosphere. Okay, the pressure of which is a pressure of 29.3 inch mercury. So this is given in inch. 29.3 in mercury, and the difference in column height is measured as 20 centimeter plus or minus 1 millimeter when exposed to an air source of at 25 degrees Celsius. So the difference in column is 20 centimeter plus or minus 1 millimeter, and it is exposed to air source at temperature of 25 degrees Celsius. The standard acceleration of gravity is present, and calculate the pressure of the air source in Pascal and its uncertainty. So we need to calculate the pressure and the uncertainty of the pressure. In this case, we will see, we know the manometric fluid is specific gravity is 0.82. So the density of the fluid is 0.82 into 996, the density of water, into 816.7. So we get 816.7 kg per meter cube for the manometric fluid density. Then we have pressure of the air, which is given 29.3 inch Hg. So we convert into Pascal, which will come out to be 9.922 into 10 power 4 Pascal. This is rho gh. We multiply rho g h in meters. You convert it into meters, and then rho is 13.6 into 10 power 3, and g is 9.81. So substituting that, you will get 9.922 in 10 power 4 pascals. Then also, you know, pressure of air or the fluid which pressure has to measure, we are given it is at temperature 25 degrees Celsius. So the density is P by RT from the ideal gas relation, P by RT. So P is, we have calculated the atmospheric air pressure 9.922 into 10 power 4. So divide by R is 287 into temperature is 273 plus 25, 298. So on substituting, we get 1.16 kilogram per meter cube. So, and then we know that the manometer, the pressure is P minus PA will be the rho GH into rho M minus rho F. So from this, we know rho M, we know rho F, we know H, we know G. So the difference can be calculated. We know the PA also to find out the pressure. So we substitute all the values. So G is 9.8 into 0.2, H is given 20 centimeter, so 0.2 into 816.7 minus 1.16. We have calculated both the density values, so we get 1600 Pascal for the difference in pressure. plus the pressure will be 1600 Pascal plus the atmospheric pressure. So 1600 plus 9.922 10 power 4, which will give you 1.008 into 10 power 5 Pascal. So this is the pressure of the air source, so which was asked to calculate, and we have also asked to calculate the uncertainty. So uncertainty on the column is, see, they have given that the difference in the column height is measured as 20 centimeter plus or minus 1 mm. So we know, so 1 mm by 20 centimeter, which is 200. For 20 centimeter we have uncertainty of 1, so that will give you uncertainty is 0.5%. So uncertainty in the column height is 0.5%, and the pressure is 1.0082 to 10 power 5 Pascal. I hope this is clear. Okay, then moving on, we have a McLeod gauge which has a volume B is 100 centimeter cube, and the capillary the bulb the volume is 100 centimeter cube, and the capillary diameter of 1 mm. Calculate the pressure indicated by a reading of 3 centimeter. What error would result if the AY or the volume of the capillary is very less than the bulb volume when that is considered? So we have given VB value, we have given the capillary diameter, and it's also said that the pressure indicated by the reading is 3 centimeter. So what error will be the difference when AY is considered very less than VB? So what will be the difference, or what will be the error will be? So that's the question. So we'll see. We know the capillary volume is pi by 4 into d square into the length, which is given 3 centimeter. So we convert it into mm. So 3 is 30 mm into diameter is given as 1 mm. So 23.6 mm cube is the capillary volume, and the bulb volume is 10 power 5. Given is 100 centimeter cube. So on converting, we multiply by 1 centimeter is 10 mm, so 10 power 3. So 100 into 10 power 3 is 10 power 5 mm cube. Then we know that the pressure relation is equals AY square by PB minus AY for a McLeod gauge. So AY square by VB minus AY, or this can also be written as Y into capillary volume divided by VB minus VC. So we substitute the relation values calculated. We know Y, which is 30, we know VC, which is calculated 23.6 mm cube. We also know VB value, so we substitute that. So on substitution we get 0.0071 torr or 7.1 micrometer. So and then if we calculate error, if we consider VB is very large compared to AY, so you can remove AY, so it will become VB. So error in calculation will be AY square by VB minus AY minus AY square by VB. So if you simplify it, you will get E as AY by VB. So the error will be the difference on that. So it will come out to be AY by VB. We know the calculation AY is VC, so we just substitute that value 23.6 by 10 power 5. So that will come out to be 2.36 into 10 power minus 4, which if you see the error is very small. So you can even consider this assumption. I hope this is clear. Okay, then moving on, we have a vacuum gauge which is used to use an LVDT, linear variable difference transformer, transducer diaphragm combination which will are shown in the figure. So the figure is given on the right. So that is the figure. This is the diaphragm figure when the pressure is applied, and this is the diaphragm, and that is which is coupled to the LVDT. So this says a vacuum gauge is to use an LVDT diaphragm combination like which is shown in the figure. The LVDT has a sensitivity of 2.5 nanometer. So the given the LVDT sensitivity is 2.5 nanometer, and the diaphragm is to be constructed of steel, which is 2 into 10 power 11 Pascal, and your Poisson's ratio is 0.3. Then with a diameter of 15 centimeter. So the diameter of the diaphragm is given. The material which is constructed, modulus of elasticity is given. The Poisson's ratio is given. We say calculate the diaphragm thickness in accordance with the restriction that the maximum deflection does not exceed 1/3 of this thickness. So you have to design the diaphragm, so find out the diaphragm thickness such that the maximum deflection which the diaphragm goes through is does not exceed the 1/3 of the thickness of the diaphragm. So that is the restriction which has been put. So, and then the next part of the question is, what is the lowest pressure which may be sensed by the instrument? So what can be the least pressure which you can measure when the diaphragm is designed such that the deflection is not greater than 1/3 of the thickness of the diaphragm? And here there is a relation given for the diaphragm. This is the deflection, and when the diaphragm which goes through, delta P is the pressure which is applied, the reference pressure, and then E T is all material property, A is the diameter of the radius of the diaphragm, and mu is the Poisson's ratio. It is all given. So the deflection can be calculated using this relation. So we have to design such that this does not exceed 1/3 of the thickness. So that's the question. So we'll see how to solve this. So we know modulus of elasticity 2 into 10 power 11 Newton per meter square. Then we know the Poisson's ratio 0.3. We know that the radius of the diaphragm, or A in the equation, which is 0.075. Sorry, the diameter is 15. I'll make a change here. I think it says diameter is 15. So radius is 15 by 2, which is 7.5 centimeter, which is 0.075 meter. 0.075 meter. So the radius is 0.0075 meter or 7.5 centimeter. Then we know that the maximum deflection is thickness by 3, thickness of the diaphragm by 3, and the difference in pressure is per as this is defined for vacuum gauge. So assuming that pressure in vacuum is 0, and the maximum pressure difference which can go is the atmospheric pressure. So we take the atmospheric pressure, because assuming vacuum is 0, so difference will be PA minus 0, so atmospheric pressure. So 1.0132 into 10 power 5 Newton per meter square. So that is the pressure. So we know all the values. We have to substitute. Y max is T by 3 into delta P, then 16 ET cube, A4 raised to 1 minus mu square. So we know 3 we multiply by 3, and we take the T cube to the left hand side and 3 to the right hand side. So relation will be T raised to power 4 into 9, and pressure is 1.013 into 10 power 5, and then A raised to power 4, which is 0.075 raised to power 4 into 1 minus 0.3, the Poisson ratio raised to square, divide by 16 into E is 2 into 10 power 11. So on simplifying, we get T is 1.692 into 10 power minus 3 meter, or 1.692 or 1.7 mm. So that is the thickness. So our sensitivity of LVDT is 2.5 nanometer. That is the minimum change in deflection which can be measured. So LVDT sensitivity is 2.5 nanometer. So this restricts the maximum deflection that the minimum change in deflection which can be measured. So a maximum deflection at 1 atmosphere equals T by 3. So maximum deflection which occurs is 1 atmosphere. So T is, we have calculated 1.692. So that divided by 3 is 0.564 millimeter. So delta P for 2.5 nanometers is, so this is deflection. We know the maximum deflection which can go through is 0.564, and which is calculated for atmosphere of 1.013 to 10 power 5. So this can be the maximum pressure. So the maximum pressure, maximum deflection occurs at maximum pressure. So 0.564 mm deflection occurs at 1 atmosphere, 1.013 to 10 power 5 Newton per meter square. But the minimum which can measure is the sensitivity of the LVDT. So at 2.5 nanometer, what can be the pressure is the question which has been asked, the lowest pressure which can be measured. So that is the least pressure which can measure. So at 0.564, it's 1 atmosphere. So at 2.5 nanometer, what is just a cross multiplication. So you get 2.5 into 10 power 9 nanometer divided by 0.564 into 10 power minus 6 into 1 atmosphere. So in this case, you will get that is 4.431 into 10 power minus 6 atmosphere, or 0.445 Newton per meter square. So this is the least minimum pressure which you can measure. I hope this is clear. I repeat, from the relation of the diaphragm for maximum deflection, and we know maximum deflection is T by 3. On substituting, we find out the thickness of the diaphragm, and the minimum pressure difference, or the least count, you can say, the minimum difference in pressure which you can measure is restricted by the sensitivity of the LVDT. So that is 2.5 nanometer, and we know that maximum deflection occurs at 1 atmosphere pressure. So at 2.5 nanometer, what will be the pressure? It's just a cross multiplication, and we can find out for 2.5 nanometer, which is 0.45 Newton per meter square. So moving on, the next question is, we have a capacitive transducer which is constructed of two 1-inch square plates separated by a 0.01 inch distance in air. So area is given as 1 inch square and the distance is 0.01 inch. Calculate the displacement sensitivity of such an arrangement. The dielectric constant of air is 1.0006. So you have to find out the displacement sensitivity for a capacitive transducer, which is made up of two plates of 1 inch square and kept at a distance of 0.01 inch, and air is the medium inside. So for that, the dielectric constant is 1.0006. From this we know C is 0.225 epsilon A by D. So 0.225 is used when this is in inch, and if you do a conversion, it will come out 0.0885 when it is in centimeter. So we know C relation. We differentiate this with respect to D, the difference in distance between the plates. So that is what will measure the displacement. So one plate is fixed, the other plate keeps on moving, so that will cause a change in the capacitance. So that is used to measure the displacement. So the variable here is the distance between the plates. So that's why differentiate C is the output and D is the input. So differentiate that with respect to D. So C relation B is known. So on differentiation we get minus 0.225 epsilon A by D square. Epsilon is the dielectric constant, A is the area. So we substitute all the values which is known, then we will get minus 2.25 into 10 power 3 picofarad by inch. So that is the sensitivity. So moving on, problem is given is LVDT has the operating characteristics shown in figure. So an operating characteristic of an LVDT is shown in the figure. We've been asked to calculate the voltage sensitivity over the displacement range from 0 to 0.04. So here in the figure you can see on the y-axis you have an output voltage, the voltage which comes, and the x-axis is the displacement. So the linear range it can move, that is given. So here we have been asked to calculate the voltage sensitivity from displacement range of 0 and 0.04. So for 0, that is 0, close to 0, it's very small voltage, you can take it as 0. And the displacement at 0.04, if you see, it's 0.6, but it's greater than 0.6, and it's 0.62. So if you see, the sensitivity will be change in sensitivity voltage divided by change in distance. So that is the sensitivity. Output by input, change in output for change in input, that is sensitivity. So delta V by delta X. So 0.62 minus 0 divided by 0.04 minus 0. So that will give you 15.5 voltage per inch. So that is the voltage sensitivity. So moving on to the next problem, we have a small cantilever beam is constructed of spring steel having E 28.3 into 10 power 6 psi. The beam is 0.186 inch wide and 0.035 inch thick with a length of 1 plus or minus 0.001 inch. So that is a cantilever construction which is given. We use a spring steel. The modulus of elasticity is given, the thickness and width is given, also the length is given. We are saying LVDT is used for the displacement sensing device, and it is estimated that the uncertainty in the displacement measure is plus or minus 0.001 inch. So LVDT is used to measure the displacement, and the uncertainty is 10 power minus 3 inch plus or minus. So the uncertainty in the bar dimensions are 0.0003 inch. So uncertainty in bar dimension is also given. Calculate the indicated force and uncertainty due to dimension tolerances when y, so the deflection is given when y is 0.1 inch. So we know the moment of inertia is this is n by I equals sorry so this is as is a cantilever beam. We know the moment of inertia, and we know the deflection is FL cube by 3 EI, that is the deflection at the end. So deflection y is FL cube by 3 EI for the cantilever beam, and from there we substitute, we know the deflection, and we have to find out the force. We have been asked to find out to calculate the indicated force and uncertainty. So force is we have to calculate. So we cross multiply and we keep F on the left, and the rest of the terms are known. So moment of inertia for a bar is pH cube by 12. So we know B and we know H is 0.035. So we substitute the values and we get moment of inertia is 6.64 into 10 power minus 7. So we substitute in the force relation, and we know E, we know I value, we also know the length. So on substituting we get force as 25.09 Newton or 5.65 pounds. So uncertainty in the force measurement can be written as this is uncertainty relation. If you remember in the I think week 3 it's taken uncertainty. So that's the relation. We know the force equation. So the variables are the breadth, height, width or height, and length. Also the displacement or the deviation. Sorry, deflection. So deflection, length, height, and breadth. So those are the variables. So the uncertainty of those are given 0.003 and 0.001. Length uncertainty is given. The displacement uncertainty of which is calculated by LVDT is given. That is also 0.001. Then the width and thickness of beams uncertainty are 0.0003. So we know the relation, the fraction change uncertainty of force is equals to WB by B the square plus you have any query? Okay, so uncertainty relation is for force is WF by F, which is W is uncertainty of the force divided by force. Same goes for the relation. So WB by B the whole square plus 9 WH by H the whole square. So the 3 comes from the H raised to power cube. So that 3, the square of that is 9. If you remember the product for if the variables are as a product, then the relation comes as the coefficient square into the uncertainty by the variable. So WB by B the whole square plus 9 into WH by H the whole square. Same for the other variables. So we know the uncertainties of the variables and the variable values. So on substituting, we get it as 0.0278 or 2.78%. So the uncertainty in force measurement is 2.78%, and the force is 25.09 Newton. So moving to the next question, we have a resistance strain gauge with R of 120 ohms and F is 2, gauge factor is 2. It is placed in equal arm bridge in which all resistance are equal to 120 ohms. The power of voltage is 4 volts. Calculate the voltage indication for a strain of 1 micro inch per inch when a high impedance detector is used. So in a Wheatstone bridge, one of the resistance is the strain gauge. All the resistance are balanced. So this is a balanced bridge with resistance of equal resistance. So 120 ohms of each resistance, and so one of the strain gauge goes under a strain of 1 micro inch per inch. So in that case, we have to calculate the voltage indicated. The supply voltage for the Wheatstone bridge is 4 volts. So we know all the resistance are equal, and it is equals to 120 ohms, and we also know the change in voltage by E is the difference in the voltages. If you take half bridge voltage from the resistance based on the currents, we calculate that it will be R1 by R1 plus R4 of the two resistances, and the other will be R2 by the other two resistances. So in here, R1 is the strain gauge resistance. So if it changes by delta R1, so R1 plus delta R1 by R1 plus delta R1 plus R4. So that is the change because of the change in resistance of the due to the strain induced on the strain gauge. So that will cause the bridge to generate some voltage, that is delta ED. So you have to measure that. So from this we take R common, R1 common, so we get a fractional change in resistance of the strain gauge. As the resistance are equal, so this will turn out to be 1 plus delta R1 by R1 divided by R1 and R4 are equal, so it will be 2 plus delta R1 by R1 minus this being equal, it will become 1 by 2. So on simplification, this will become delta R1 by R1 divided by 4 plus 2 into delta R1 by R1. So the resistance change is calculated from delta R1 by R1 is F into epsilon. F is the gauge factor, epsilon is the strain. So 2 into 10 power minus 6, because strain is 1 micro inch per inch. So on substituting, the fraction change in resistance is 2 into 10 power minus 6. We substitute that in the expression, so we will get 2 into 10 power minus 6 by 4 plus 2 into 2, which is 4, 4 into 10 power minus 6. So this will give you 0.5 into 10 power minus 6. That is the fractional change in the voltage with respect to supply voltage. So we substitute that by supply voltage, which is 4 volts, which will give you 2 microvolts. So that is the change in voltage or the galvanometer, which is of the Wheatstone bridge, that will indicate a voltage of 2 microvolts. So that's all for today. If you have any doubts, I'll be happy to answer. Sorry, you have any doubts, or we can close the session. I'm waiting for your response. Do you have any doubts? So as there are no doubts, we'll close the session.